Welcome to Flink Forward 2021. We are Jan, Levin and Joscha, and we want to talk today about how we used Flink to solve our problems. But before we talk about Flink, we want to introduce ourselves. We are Neuland. We are a company in Bremen, Germany, Bremen and Kiel in Germany, and we got about 140 employees. We were founded in 2006 and grew ever since. I'm Joscha. I started at Neuland in 2016, and the first time I faced the thing I'm going to talk about, called fraud, I experienced in 2017 and focused on that topic ever since. But what are we doing in particular besides fraud? We build custom solutions for several customers, and our target is high-performance e-commerce solutions for different customers in Germany. And when we started that, we learned that there are some reappearing problems, like search algorithms, recommendations, fraud, and a lot more. And since we think e-commerce expert should be able to handle all topics, we learned a lot of those topics. And one of those topics is fraud, and I'm going to talk about that today. When we talk about fraud, we talk actually about fraud prevention. And why do we talk about that? We learned that the more successful shops are, the more fraudsters will be aware of those shops and try to make money with those. And since we have a lot of customers who have shops, we are in a favorable position. We can gather information from multiple sources and use that knowledge to distribute our knowledge as well and help all of our customers to prevent that fraud. Since there is no perfect solution out there, that is not that easy. There are different attempts how you can do that, and we are talking today about why it's not easy and how you could handle that problem. What is the challenge? Attackers will always leave some trails. If you look at the real world, if you get to a shopping mall and you got a detective there, he will look out for thieves and will look for every detail. But they won't see anything. They got bad viewing angles, bad camera angles, and can't see anything they're doing. And there might be some really important movements they do. On the World Wide Web, we don't have the problem, because every time a fraudster communicates with a shop, he needs to communicate with an API, and that will leave some trails. And every trail can be useful, and every trail is visible. So compared to the real world, on the World Wide Web, we got an advantage. We will see everything, but this challenge remains the same. What is good traffic and what is bad traffic? But why do we see everything? In the World Wide Web, we can assume that the customer will use a browser, and if you use a browser, you need HTTP to communicate with the shop. And communication is really necessary, because otherwise you can't do anything at all. And if you use HTTP to communicate with shops, you will leave some trails. You will leave your IPs, you will leave some timestamps, some URLs, and it's easy to trace some actions by using those data. Attackers are obviously aware that they leave those trails, so they will take some countermeasures to hide their identity by using VPN or distribute their attacks about bot networks, so you can't detect their identity. But detecting their identity isn't our goal at all. We want to trace the activity to be able to distinguish between bad and between good traffic, because that's the thing we want to do. We don't want to identify the attacker. It's enough if we can prevent the fraud. But how do we do it? The first thing we know is, obviously, we start with quantitative data, which is just a session, which is just a lot of traffic, and we want to know how to use that data to actually identify potential fraudulent transactions. And to do that, we need to aggregate sessions first. If we want to aggregate sessions, we can use several data, but in the end, we will have a session, and a session is, in most cases, a single user. We can trace and try to find anomalies. And that's the next thing we want to do. Anomalies can be hidden anywhere. Anomalies can be hidden in sessions, they can be hidden in traffic, in global traffic, and they can be hidden between sessions, which you just can see if you compare sessions to each other. And what we are doing is looking for any anomaly we can find, because any anomaly can help to distinguish between good and bad traffic. And if we want to distinguish between good and bad traffic, we want to rate everything. We want to rate every session and classify it. And when we classify a session, we really need to be careful, because we don't want to classify good sessions as bad and bad sessions as good. So we will really be careful if we classify a session. But in any case, if we got an anomaly, sessions might be rated worse than others, but not any anomaly will cause a bad rating, because if you measure a lot of anomalies, you will find a lot of anomalies, but what anomalies are the bad ones is a really question which we are facing. And if we have a session, we want to map use cases too. If we just see there was a login, we don't know which login it was, it's useless. So we need to map the login to a transaction. In our case, transactions are unique IDs which identify certain actions, like a login attempt, like voucher code which was validated, or everything which might be used to do fraudulent activity. And that's the actual thing. We want to know which use cases happened during which session and what transaction IDs were used in that session, so that we can use the data later on to mitigate or prevent fraud. And that's the last thing we want to do. We want to distinguish good and bad transaction, because just if we can do that, we are helpful to our customers, and customers can take countermeasures to handle those. But before we dig deeper into those topics, Jan and Levin will tell us about the architecture and the processes we use to aggregate sessions and rate it before I continue my part. And Jan will continue.
Okay, hello, my name is Jan. I work for almost 10 years at Neuland in various roles, currently as a data engineer. And I would like to show you why we chose Flink specifically for this task. First of all, as most of our customers are large e-commerce shops, we are dealing with a high volume of data. Then fraud detection, as you have heard and will continue to hear, is a highly complex task. And we want to do the fraud detection in real time, because the information that you get frauded 3 hours ago or 1 day ago is of not much use. And so for us, the selling points for Flink were the highly flexible but convenient programming model, which helps us capture the domain of fraud detection. Then Flink is field tested with the throughput that we need. And also there are a lot of applications in Flink running 1 or 2 orders of magnitude higher than we do, and so we can have the assurance that we can scale up if we need to. Flink has reliable and tested exactly one semantics that we need to build session aggregations that we can rely on in the evaluation. And one major selling point for Flink is the community support and the comprehensive documentation. We chose specifically stateful functions for Flink because for us, fraud detection at its core is an event-driven task. You want to re-evaluate each session after each new event, because each new event can potentially put a session in a completely new light. And another core design goal of ours was to let the different experts focus on what they can do best. A Flink or ops specialist doesn't need to concern himself with security knowledge or security patterns or detection patterns or whatever. And a security specialist doesn't need to concern himself with stream processing, core logic, or Flink operations. And so Flink Stateful Functions offered us a possibility to separate both of these application fields. And we need the ability to react fast in case of emerging new attack patterns that we can deploy the Flink Stateful workers with zero downtime within a couple of minutes or a couple of seconds roll out a new fraud detection pattern or a new machine learning model. Let's look at the architecture. What you see here is a rough conceptual overview of the bot spotter application. Starting from the left are the incoming data sources. Currently the backbone of our fraud detection are the HTTP logs, because they lend themselves very well to build an aggregated view of a session and to see what's going on in the whole shop the whole time. But we can incorporate any additional event source, like a mouse click stream from the website, for example. In the box at the top, you can see the Stateful application. The one part of it is the session aggregator, which builds an aggregated view of each session from the HTTP events and sends this aggregated view to the business logic Python workers, which you can see on the right of the box. These evaluate the session, score them, and send in session evaluation back to the session aggregator. And from there, the evaluations go to the output layer. And if you think about it, where potential information about fraud in a session comes from, you can see that it can come from the session itself, but it can also come from the global shop state. For example, if we see a session with a failed login attempt on this first event, this is not suspicious in itself. But if we look, for example, then at the global shop state and we see from the same IP address we have 1,000 failed logins in the last 5 minutes, then we see this is a fraudulent session and this information is not contained in the session itself, but in the shop state. And so we built a separate vanilla Flink application, which is called the shop state aggregator, which aggregates metrics about the shop in real time, syncs them to a Redis, and so the business logic can access them whenever it needs to score a session. Below the line is the output layer. As it is drawn here, it's a default configuration of the bot spotter. Out of the box, we will deliver it like so, where we put the session evaluations and additional information about the logins in streams and sync them into a database. And then we provide them to the customer via a JSON API and a back office, which we will look at later. But due to the modular structure of the whole application, anything below the dotted line is basically up to the customer, and we are able to integrate with any existing back office infrastructure that's already there. And my colleague Levine will now walk you through the details of all the components.
Hi, I'm Levine. I'm a backend software developer at Neuland for almost 2 years. And I like to talk a little bit more about our infrastructure. Because most of our customers run the application inside AWS, we are also compatible with it. As shown, we have 5 components running inside the AWS. A Postgres to store results, a MSK to exchange messages, and a Redis for the shop state aggregator. A S3 bucket for the checkpoints of Flink, and an EKS. Inside the EKS runs our application code. To operate the bot spotter, we use things like Helm, Datadog, GitLab CI, and Terraform. All these technologies are widely used and ensure we fit into the existing infrastructures of customers. It supports continuous delivery, so we can deploy any component at any given time. Terraform is there to ensure that the infrastructure is easily to integrate and also easily integratable in other infrastructures from customers. So let's take a closer look on the parts from the bot spotter where the magic happens. The shop state aggregator is a vanilla Flink application that is used to count events and features that occur throughout the overall shop traffic. A custom process function counts events and features from the Ingress Kafka stream and stores and increments counters inside the AWS-hosted Redis. The inside looks as follows. Some specific counters represent use cases, like a login or a registration for a newsletter, which are later important for the evaluations of sessions. We count things like the total number of requests in the past X minutes and the total number of requests from a specific IP, for example. Different counters for different use cases helps us to identify anomalies and fraud inside the shop traffic. The second part of the bot spotter we'd like to show you is a session aggregator. The session aggregator is a Flink Stateful Function operating on a Kafka stream as well. Like the name says, it aggregates a Kafka message stream to a session object and communicates with the session evaluators and has an outgoing stream of results. We are using the session ID as the key for the stateful function. We exchange and aggregate numerous features from Kafka, from the Kafka messages, like the total number of events, the number of logins, the duration of the session, and many more. The aggregation is not limited to consume just front-end proxy logs. It can also take other streams into consideration to enrich the session object. It sends the aggregated session object via an HTTP call to the session evaluators and publishes the results over the Kafka at the end. The third part is the session evaluator. The session evaluator is called via HTTP and evaluates if the session is fraudulent and sends the results back to the session aggregator also via HTTP. It can It also can gather information from the Redis. It evaluates every incoming session aggregation object with heuristics and machine learning models, where it can use a lot of different heuristics and machine learning approaches to determine fraudulent sessions. Additionally, heuristics or machine learning approaches can be use case specific, so they're not used for every evaluation. Domain knowledge can easily be described over heuristics, where more complex approaches can be described over a machine learning model and can be taken into consideration. And now we would like to talk a little bit more about our back office, and Jan will tell you a bit more about it.
Okay, let's take a look at how we handle potential fraud in the back office that we deliver out of the box with the bot spotter. What you can see here is a functional wireframe of the back office. In practice, this would be labeled and layouted after customer specifications, and also functionalities can be added or removed as requested. But what we want to do here out of the box is we want to enable customers to work with the insights generated by the bot spotter, because we know that data is only as valuable as its presentation layer. Our fraud back office enables users to query and select suspicious sessions, view advanced visualizations about the fraud attacks going on in the shop, and to trigger with the press of a button business processes for accounts under attack. And I think it's important to mention here that we explicitly do not implement defensive measures or business processes that deal with fraud. The bot spotter, the scope of the bot spotter is to offer the ability to recognize fraud, to make it visible, and to flag it in real time. But how to process that information is up to the individual business in their respective domain. Of course, we have an opinion on that, and we also offer consulting on that. But in the end, this is not in the scope of the bot spotter and would be a completely different domain. Let's take a look at how we actually find fraud.
Now, since we learned how we structured our processes and how we build our infrastructure, we want to talk how to find fraud. But before we talk about how to find fraud, we want to talk about attackers. Because attackers got their issues and business models as well, and if we are aware of those, we can handle those better. If we talk, for example, about an account takeover, we talk about 11 billion credentials which leaked until today. And attackers will use that credentials because they know some of those are valid on any shop. And they also know that there's at best a chance, 1 in 1,000, that those credentials will work. So they need millions of credentials just to take over a few accounts. Obviously, if we got millions of login attempts, we will see an anomaly. And this one is really important to detect, because we can help our customers by detecting taken accounts and saving those accounts from any further damage. Next thing is promotion abuse. In promotion abuse, if you got 70 million possibilities for promotion codes, and attackers know several thousand of those are taken by actual promotion codes, they just can try to validate as much promotion codes as possible, and with some time they will find some valid codes. And this obviously will to leave a lot of anomalies, because they need a lot of failures to track down single working codes. And at last, crawling won't cause a lot of failures. The attackers will track a lot of products in a shop just to see what kind of products are there, how is the stock, or how are the prices. But there's also the use case, at least during the last years with crypto mining, we learned GPUs are also variable, so they just trace graphic cards and see which has stock again, which is cheap, and try to find the best time frame to buy those. There's obviously a lot more of potential fraud, but we'll leave it at that for today, because otherwise we will talk about that way too long. But now, when I talked about fraud, I also talked about anomalies. But if we want to detect anomalies, we have to know certain things, like what is our current traffic, what is the traffic when we aren't attacked. If we don't know how our traffic looks like when we aren't attacked, we won't ever be able to detect an attack either. So we need to distinguish between two different kinds of traffic. Like, what is common traffic? What is your daily traffic? What does it look like on a weekend? If you don't know that, you won't be able to detect anything. Then you got uncommon traffic too, like on Black Friday, when you know, okay, I got more traffic on that day because a huge amount of sales, and this traffic just several times higher than usual, but that's no attack at all. And what's really important is what is not uncommon traffic anymore. When we really see we didn't expect it, we can't explain that with normal customer behavior, in that case we know we most likely got an attack. But how does it look like? Well, here we see a graph over several days, and we see some regular patterns, and at Saturday morning we see a spike. And that spike is obviously an attack, an obvious attack. So we should note at this point that this spike is a really small attack. Usually the spike is so huge that the actual curve with the normal traffic will disappear completely because it's several times higher. Or the attack can last over several days. So you got not just an anomaly for a small peak, you got anomalies during a large period. And during that period you get your common traffic too, but you won't be able to distinguish it if you can't distinguish the good and the bad traffic at all. And that's where our challenge begins. We want to distinguish good and bad transaction. We want to know how to distinguish the traffic. So we always begin at an anomaly. Without anomalies, we can't do anything. Up until now, we just got a curve, and the curve won't tell us which use cases are affected. A curve won't tell us what transactions are affected. So we need to transform that. So we need to identify the use case. And additional to the use case, we need to identify sessions. And if we got use cases and sessions, we can see if there was an use case which might be fraudulent. And we want really to identify those fraudulent use cases, to map those to unique IDs, so the shop can take care of those and make countermeasures to prevent any damage or at least mitigate it. To do that, we need to take a look deep into the session. And if we want to take a look deeper into the session, we need first to learn how to aggregate a session, because this really might be tricky. We got IPs, we got cookies or other identifiers like logins. But IPs change, cookies might run out, or logins as other identifier might expire. Or in a bad case, we use a cookie which is really valid for a long time. Like if you got a session which started with a cookie 2 weeks ago and the cookie is still there, and you continue that session and say there's an anomaly because there was a huge gap between 2 requests, you just had a bad way to aggregate a session, and you should have treated those as different sessions. In that case, you actually might have caused a harmful anomaly for a completely normal customer, and you totally want to do that. So aggregating sessions can be tricky. If you do it in the right way, you can really have good data, and if you do it in the wrong way, you might cause some anomalies which will totally ruin your data and create a lot of false positives. Next, we want to classify sessions, and we have several ways to classify a session. We can rate sessions by the performance data. If we got 10 product detail page calls in just 5 seconds, this just might be a customer who is interested in a certain product and just want to compare some products. If we got 200 product detail calls in 5 seconds, this is most likely not a normal customer anymore. This might be a high performance bot which just try to crawl things. So performance data might be a good thing to distinguish bots and normal humans. Next thing is, if we don't got those performance data, just normal request, we still can rate it for plausibility. If we use a browser, browsers will load images and some AJAX calls for content which is loaded later. And if we got a script, for example, who doesn't care about those images and AJAX call at all, those requests are missing. And if we got a session which doesn't contain any of those requests, we know this is most likely script and no browser at all. This might be a good thing to distinguish good and evil as well. And at last, we can rate sessions compared to each other, because just when we put those into context, they're useful. If we think about a login, we know about 80 to 90% of logins are successful, so we got 10 to 20% of failed login attempts all the time. But if the login attempts success rate drops to 5 to 10%, we know, okay, we might face an attack. If we see additionally that the login attempts multiplied in the last time frame, then we really know there's someone who just want to validate data. So a failed login attempt alone might be not a bad thing at all, but if we got multiple failed login attempts and put into context, we can really extract a lot of data. And so we see there are several ways to rate a session, and there's some more. But in the end, we want to rate a session to do one thing. We want to identify transactions, because that is, as I already mentioned, the thing we want to do. Just if we can identify a transaction and say, we had a login attempt during a time frame where a lot of login attempts failed, and we found some other data which are clearly distinguishable from good data, we can actually say those logins, those successful logins during the time frame were a good thing, and for those accounts who were logged in with those patterns, really should take action to prevent any further damage for us and the customers as well. So identifying transactions is really the important thing. And we focus on identifying transactions because we learned when it comes to mitigation, all shops have different ways to treat those. Some say if account was taken, we reset the password. Others says we need to contact the customer immediately. Others says, okay, we just block the account for the rest of our lifetime and it can't be used anymore. And because all shops should know how to treat their customers the best, we leave it up to those. But all depend on the same thing. They depend on data where they can distinguish good and bad transactions. And so we totally focused on providing those information so shops are able to take care of fraudulent activity on their own. And during that journey, when we had anomalies and tried to extract transactions, we faced some issues when we used Flink, and we have a lot of lessons learned. And those lessons learned aren't a thing we want to keep for ourselves. We want to share our experience. And that will be done by Jan and Levin next.
I like to talk a little bit about the lessons we learned. So some of the things we learned were that unlike the edge case, no matter how low the chances are, will happen and can lead to performance problems. The separation of business logic and stream processing was a good approach. Each expert can focus on their field without too much knowledge about the other parts. And protobuf was a good choice to define the exchanged messages. Interfaces were easy to implement and it helps to achieve a good design. We came to the conclusion that RocksDB backend and an HDD disk don't go well together. So if you have a state that changes often and has quite a big size, it is advisable to hold it in memory if possible, or use an SSD disk. So tuning a Flink cluster is most likely a science, but it is an art as well. We have also made some experience with the Flink community, about which Jan would like to tell you something.
And as closing words, we like to thank the Flink community. We found out during the project that it really is as awesome as advertised. It has lots of active users. You can get helpful answers to almost all of your questions in less than a day. And you can see regular contributions from Flink core developers all over the place. That's really great. And especially we would like to thank Igal, Konstantin and Nico from Bavarica for sitting down with us and reviewing our application when we needed it. That was a great experience the whole time, and we hope to continue the collaboration in the future. And that's it. That wraps the talk up. Thank you very much for listening. If you want to know more about the application, please visit the site. But we will also be there to ask questions after this talk. Thank you very much. Goodbye.